Hello students, right now we'll discuss temperature dependence of a rate of a reaction, and within this we'll discuss Arrhenius equation. So let's see. With rise in 10 degree temperature the rate constant nearly doubles. So here you see, in decomposition of dinitrogen pentoxide, half-life of the reaction is 12 minutes at 50 degrees Celsius, 5 hours at 25 degrees Celsius, and 10 days at 0 degrees Celsius. So you see, with increase in temperature, the half-life gradually decreases. Here it was 10 days, then it is 5 hours, and it is only 12 minutes. Are you observing? So you see, next we'll discuss about Arrhenius equation. So what is Arrhenius equation? The temperature dependence of a rate of a chemical reaction is explained by Arrhenius equation. That means how rate of a chemical reaction is affected by temperature. So let's see the Arrhenius equation. Rate constant K is equal to A into e to the power minus EA by RT, where K is rate constant, A is Arrhenius factor or frequency factor, EA is activation energy, R is gas constant, and T is temperature in Kelvin. So here Arrhenius equation is a quantitative relationship between rate constant and temperature. You see, only we will previously we are discussing with increase in temperature the rate of the reaction will increase, but here it gives the quantitative explanation. So in Arrhenius theory, it explains that the products are formed through intermediate or through activated complex. We'll go for the example. Here you see, hydrogen reacts with iodine to form hydrogen iodide. So you see, this is hydrogen molecule H single bond H, iodine molecule I single bond I. So what happens here? Here you can see the intermediate it is formed. That means this bond undergoes fission, that is bond cleavage or bond breaking. Simultaneously, a bond is formed between what? Hydrogen and iodine. So here you can see the activated complex, or the here you can see the intermediate. Okay, and finally product is formed. Clear? Let's see the graph. Here you can see the reactant hydrogen and iodine. The energy of the reactant is this much. Then what happens? It gains some sort of energy and its energy value gradually increases. And if you want to form the product, then you have to supply sufficient amount of energy so that it will overcome this minimum amount of energy barrier. If it gains this much amount of energy, then only it can form the product. Otherwise the product will not be formed. So the minimum amount of energy required for the reactant to form products is known as threshold energy. Okay, and here the activated complex lies or the intermediate lies. So in order to understand this, we have to take a simple example. You all are in class 12th, and as a student your mind is not at all blank. Just remember one thing, no one in the universe is having zero IQ. They have some sort of information, they have some sort of knowledge in their brain. Okay, so in order to pass, you need minimum amount of your percentage. That minimum percentage, if you will get, then only you can finally you can certificate will be provided to you, your 12th pass. Clear? Similarly, in this case, the same thing is threshold energy. That means you see, you have this amount of energy and you need this much amount of energy. So the difference is this much. This difference is called activation energy. So it is the energy of the reactant and this is the threshold energy. Okay, so the difference between threshold energy and the energy of the reactants, that is known as activation energy. So let's go for the definitions. What is threshold energy? It is the minimum amount of energy the reactant should possess to undergo chemical reaction to form product. Next is energy of the reactants. What is energy of the reactants? The reactant possesses definite amount of energy, that is called energy of the reactant. Next is activation energy. It is the extra energy required by reactant molecules that results into effective collision between them to form the product. That means this is the extra amount of energy. This is the extra amount of energy required by the molecules that results into effective collision to form the products. So activation energy is equal to threshold energy minus energy of the reactants. Okay. Now we will discuss Maxwell-Boltzmann distribution curve. So this is the Maxwell-Boltzmann distribution curve, and what information does it provide to us? So let's discuss. Here the curve is plotted between which two parameters? Fraction of molecules, that is Ne by Nt, number of molecules having energy E, and total number of molecules. With what? With kinetic energy. So you see, this is the peak of the curve. This peak of the curve represents what? Peak of the curve represents energy possessed, or the kinetic energy possessed by the maximum fraction of molecules. This energy is known as most probable kinetic energy. So this is the most probable kinetic energy. What is most probable kinetic energy? You see, this is the peak. Peak refers to maximum number of molecules or maximum fraction of molecules is here. Here the number of fraction of molecules gradually increases, and this is the maximum number of molecules. That means the energy possessed by maximum fraction of molecules is known as what? Most probable kinetic energy. As you move from left to right, the kinetic energy value increases. So from this curve we can see that the fraction of molecules having less amount of kinetic energy is low, and the fraction of molecules having more amount of kinetic energy or high amount of kinetic energy is also low. And most of the molecules, they are in between. So this is the broad area in which maximum number of molecules they lie. Okay. So right now we'll discuss temperature dependence of rate of reaction. So what is the meaning of this statement? That means if we'll change temperature, how the rate of reaction will vary. So let's see. We know Arrhenius equation was K is equal to A e to the power minus Ea by RT. Taking ln of both sides, we get what? Ln K is equal to ln of A into e to the power minus Ea by RT. And we know, suppose this term is x, suppose this term is y, then right now it is ln x into y. So what is the formula of ln xy? The formula of ln xy is equal to ln x plus ln y. So putting this formula here, we'll get the expression this. So ln k is equal to ln a plus ln e to the power minus a by rt. You see here, this is in exponent position. So ln e to the power x is equal to how much? Ln e to the power x is equal to x ln e. We'll put the formula. This is the exponent and it will come to the coefficient position. So it will be how much? Minus Ea by RT ln E, and we know ln E is equal to how much? 1. That means this expression will be how much? Minus Ea by RT. So you see ln K is equal to ln A minus Ea by RT. Okay. If we will take this expression for different temperatures at T1 and T2, then the expression will be ln K1 is equal to ln A minus Ea by RT. Why? Because at temperature T1 the rate constant will be K1. So this expression, if we will take temperature T2, then that constant will be K2. That means the expression will be ln K2 is equal to ln A minus Ea by RT2. Right now, if we will subtract equation 3 from equation 4, then what will be the expression? Ln K2 minus ln K1 is equal to how much? Ln A gets cancelled, because if we will subtract this from this, obviously it will be cancelled, and finally we will get minus EA by RT2 minus EA by RT1. So let's simplify it. Ln K2 minus ln K1 is equal to how much? Ln X minus ln Y. What is the formula? Ln X minus ln Y is equal to ln X by Y. The expression becomes ln K2 by K1 is equal to EA by RT1 minus EA by RT2. Okay? If we will simplify this, you can see in both these two terms, EA by R is common. So taking EA by R common, it becomes 1 by T1 minus 1 by T2. So let's simplify further. Ln K2 by K1 is equal to EA by R. Taking LCM is T1, T2, and then simplifying T2 minus T1. That implies if we will convert ln into log, then how much it will be? It will be 2.303 log K2 by K1 is equal to EA by R T2 minus T1 by T1, T2. Okay, so you see this side 2.303 is multiplied. If we will take it to the right side, it will be divided. So the final expression becomes log K2 by K1 is equal to EA by 2.303 R T2 minus T1 by T1, T2. Okay, now let's discuss the curve. There are two curves, and these curves are plotted between fraction of molecules and their kinetic energies. The first curve is plotted at T Kelvin and the second curve is plotted at T plus 10 kelvins. That means here temperature is raised by 10 kelvins. Before going to discuss this curve, you should remember 2 points. First point is that the area under the curve gives the fraction of molecules. More is the area, more is the fraction of molecules. Second point is that the molecule will undergo chemical reaction if the energy possessed by the molecule will be equal or more than the activation energy value. So you observe right now the first curve, the area under the curve more than activation energy is this much, but at T plus 10 Kelvin the area under the curve is this much. That means here you can find the area under the curve having more energy than activation energy is more. That means the curve is flattened. That means more number of molecules will undergo to form the products. So when the temperature increases, the number of molecules having energy more than activation energy increases and they undergo chemical reaction to form the product. Now we will discuss effect of catalyst on the rate of a reaction. That means how catalyst puts effect on the rate of the reaction, whether the rate of the reaction will increase in presence of catalyst or decrease or will remain constant. So a catalyst is a substance which increases the rate of the reaction without undergoing any chemical permanent change. According to intermediate complex theory, this is a theory relating to catalyst. A catalyst participates in reaction by forming temporary bonds with reactants resulting in an intermediate complex. That means what is the meaning of this? Catalyst takes part in a chemical reaction and forms temporary bonds. In surface chemistry chapter we will discuss in detail. So you see, for an example, A reacts with B to form AB. This is uncatalyzed reaction. But if it undergoes catalyzed reaction, then the equation will be A plus B plus C, where C is catalyst, and the intermediate will be ABC. That means C undergoes formation of a temporary bonds, and finally C is regenerated and AB gets the product. This is a catalyzed reaction, and here the rate of reaction becomes very fast as compared to uncatalyzed chemical reaction. Catalyst provides an alternate pathway or a reaction mechanism by reducing activation energy between reactants and products. You see this curve and this curve. This is the reaction pathway without catalyst, and this curve represents reaction pathway with catalyst. So without catalyst, you can see the activation energy needed for this is very high, but for this the activation energy needed for the reaction is very low as compared to this. That means it provides an alternate pathway, and the potential energy barrier is very low, so that it can be overcome easily, and the reactant can undergo chemical reaction to form the product very easily. Okay, next we will discuss characteristics of catalyst. What are the characteristics? A small amount of catalyst can catalyze large amount of reactants. Number 2, does not alter Gibbs energy. Equilibrium is attained quickly in presence of catalyst. That means it increases rate of forward reaction, it increases rate of backward reaction, so that the equilibrium is attained quickly. It can catalyze only spontaneous reactions. That means it will not catalyze non-spontaneous reactions. Next, catalysts are highly specific. Means what? One catalyst cannot be used for several reactions. One catalyst for a particular type of chemical reaction. It never starts the reaction which has no tendency to proceed. Now we will discuss collision theory of chemical reactions. This theory was put forward by Max Stross and William Lewis in 1916 to 1918. What are the assumptions of this theory? The reactant molecules are assumed to be hard spheres, and reaction takes place only when the molecules collide with each other. So what is the meaning? So you can see this is a molecule, this is a molecule, this is a molecule. These molecules are supposed to be very hard spheres, and the reaction will take place when these molecules will collide with each other. They will collide this, they will collide with this, as a result of which what will happen? The reaction will take place. The number of collisions per second per unit volume of the reaction mixture is called collision frequency. That means what? The number of collisions made per second per unit volume is known as collision frequency. And we have already discussed activation energy plays an important role in the formation of a product. If the energy less than activation energy will be there, then no product will be formed. So let's see a hypothetical chemical equation. A plus B forms products. Here rate of the reaction is equal to how much? Rate is equal to ZAB e to the power minus EA by RT, where ZAB is the collision frequency, e to the power minus EA by RT is the fraction of molecules having energy equal to or more than EA. Let's see the Arrhenius equation. We have discussed several times. K is equal to A e to the power minus EA by RT. Right now you compare this equation and this equation. You can see rate, K is the rate, and here K both are same, rate constant, and this part is also same. That means they differ. A is replaced by ZAB. So A can be related to collision frequency. Remember, all the collisions do not form products. Collisions having sufficient energy means minimum threshold energy, and proper orientation can form the products. So a new term came into play. Proper orientation should be there. So you recall what? SN2 reaction mechanism. How the approach in proper direction helps in formation of the product. So let's see an example. Formation of methanol from bromomethane. Here bromomethane is there, and here a hydroxide ion is there. This hydroxide ion will attack the carbon of bromomethane to form the substituted product, that is methanol. So let's see how improper orientation and proper orientation helps in formation of a product. You see, this is the improper orientation. This refers to the proper orientation. In a proper orientation, what you will see? Carbon is there, this side bromine is there, and OH minus approaches towards bromine. So it contains fractional negative charge, it has negative charge. There will be repulsion and no reaction will take place and no product will be formed. But in the second case, OH minus approaches just opposite side to that of bromine. Then what happens here? OH minus approaches and forms an intermediate with a bromomethane and finally forms the product. Okay, that means proper orientation also plays an important role in the formation of a product. So the expression for rate constant is changed using another parameter, that is P. P is the orientation factor. So the rate becomes P into ZAB into e to the power minus EA by RT, where P is the orientation factor, ZAB is the collision frequency, and EA is the activation energy, R is gas constant, T is absolute temperature in Kelvin. Okay, and here limitation of this collision theory is that it ignores the structural aspect. Thank you for watching.